Hello, everyone, and welcome to another week of cybersecurity CERIAS seminar. Today, it's a pleasure to introduce Maxim Aaron. He is an early career scientist in A4 Los Alamos National Laboratory, advanced research in cyber system division. He graduated from University of Maryland, Baltimore with a undergraduate bachelor degree in computer science and also a master's degree. And he's currently pursuing his PhD at UMBC, University of Maryland, Baltimore County, at Dreams Lab. His research interests are in the intersection of machine learning and cybersecurity. So again, if you have questions during the talk, please write them down in Q&A section. Maxim, please take it on.
Thank you so much for the introduction and also for the opportunity to give this presentation. Yeah, so my name is Maxim Aaron, and today I will talk about tensor decomposition methods for cybersecurity. Before we start, though, I have a question for you guys on the audience. Let's say I give this presentation and then you have some questions. Would you prefer, if I didn't know answer to a question, that I say I don't know or take a wild guess to your answer? Maybe on the chat, or if you like to unmute. Vague, okay. I don't know. Yes, I think the same way. For a wild guess of one of them. Perfect. Well, I believe the same way that the answer I don't know should apply to machine learning models. When they're, instead of them confidently giving us a decision which might be incorrect at specific scenarios, it's cheaper and safer if they say, I don't know. So one of the methods I will present today will have the ability, it does have the ability to say, I don't know. But let's get there one by one. So tensor decomposition methods, it's like a Swiss Army knife. You can apply to many, many different things in cybersecurity, from network anomaly detection to user behavior analysis, malware analysis, detecting families, separating files for executables from benign samples, for data, using it for data privacy with federated learning, applying it to critical infrastructure, things like power grids for detecting anomalies to prevent failures, credit card fraud, and so forth, a lot of areas. And the things that I will present today will be us applying these methods to all of these areas, and they're all published and they're patented and with R&D 100 awards. So we're presenting things that have been published out there. And one of the methods that I will present today is the one that can say, I do not know. And we are holding a world record on classifying the largest number of malware families that are out there. So it's fun stuff. But let's get there by first talking about what is a tensor decomposition. To do that, we can first look at what is a vector. It's a one-dimensional array. In Python, you can represent it as a list. In what is a matrix? It's a two-dimensional array. You have, let's say in Python, you can represent it with a NumPy array. Tensor is anything with 3 or more dimensions. So here, for example, you have a 3-dimensional tensor. When you have a matrix, you can use this matrix from, for example, data of user authentication events. So one of your dimensions on this matrix could be users, and the second dimension could be, for example, the devices you're authenticating to. And the entrance here will be how many times you authenticated to that device. So this user authenticating to that device. Let's add one more dimension here. Let's say we still have user device, and let's say put success. For example, if you're like me, you put your password wrong all the time. So if the first dimension here is like fail, you're going to have a lot of entries here. You're putting your password wrong. So you're kind of like adding more information to your data to represent in a multi-dimensional way so that you can capture more complex details. And that's the goal of it. And once you have this large multi-dimensional data, how do you extract these patterns that are useful out of it so you can use for decision-making tasks? Well, one way to do it is called CPD decomposition, where your original multi-dimensional array is factorized into what it's called rank 1 tensors. So each of these red boxes over here is a rank 1 tensor. So my green latent factor here from the first rank 1 tensor will represent the patterns on my first dimension, which is M. And the purple one over here will represent the latent patterns for my second, and the blue one is representing the latent patterns for my third dimension, and so forth. You can have more than 3 dimensions, but throughout this presentation, we're gonna use 3-dimensional tensor to just make it easier for visualization. Otherwise, it's going to be really difficult for us to think about how a 4-dimensional tensor look like. So this is a nice way to show it. And each of these rank 1 tensors going to have some kind of useful information. For example, if you're factorizing that tensor we looked at of user authentication events, perhaps this first rank 1 tensor is showing you the activities on work hours, while the rank 2 tensor is showing you activities on the weekends, for example. And it is doing that in an unsupervised manner. So you don't need labels for it to find these useful information. So I've been keep saying hidden patterns that are useful. What do I mean by these hidden patterns? I have a really funny example that I took from my advisor, Boyan Alexandrov. So did you know that with the increase in shark attacks, ice cream consumption increases? So this, if you assume this as an observable variable, there's this kind of funny thing going on there. Is this a useful information though? Perhaps not, but there's maybe another hidden information that is more useful, that is the increase in temperature. Increase in temperature, more people eat ice cream, people go to the beach, so more shark attacks. And that's the useful information that we want to extract from our really large tensors with all the mixed patterns. Mixed patterns. So to be able to accurately model the data, I need to separate these mixed patterns. But what do I mean by separating these mixed patterns? So let's say your data is this image. There are several mixed useful information here. Some of them are kind of like mixed. So you have this heart light here, you have the Milky Way in the background, and let's say the other stars around, like here on the corners, are the background noise, and maybe the lights from the city here is background noise. So we want to separate all the background noise and just get the useful information. So when we say accurate data modeling, what we mean is get the useful parts from our data, in this case this heart with the line and the Milky Way. But further, we want to unmix the mixed signals. So this heart has mixed signals for the line around it and the heart in the middle and the line afterwards. So when we say unmixing these mixed signals accurately, it means we want to be able to separate all of these mixed features from our data set. And we do this with what's called automatic model determination, using stability and accuracy of the solution together to estimate the number of unique features I need to extract from the data set. And all of those, using tensor decomposition, automatic model determination, and other features allows us to accurately model the data and perform advanced anomaly detection capabilities that surpasses the baselines that we looked at, which were both supervised and unsupervised while we are doing this in an unsupervised manner. So our first application is detecting anomalies. It's an important problem. It's an expensive problem, and according to your reports, only low percent of the anomalies there generate alerts. So we are missing many. So it's an important problem that needs to be addressed. In the past, traditional anomaly detection methods based on, let's say, user behavior analysis looked at matrix factorization approaches, and they have successfully with great accuracy scores detected anomalies. But when we do matrix factorization, our information is limited on the two-dimensional space. So we want to be able to include more information to capture more complex details. And if other methods like supervised traditional machine learning approaches, they're black box approaches, and then they often need large quantities of labeled data. But that is difficult for anomaly detection because anomalies, as its name goes, they're anomalies. There are only few samples in a very large data that we are trying to detect. So here, tensor decomposition is useful because we are capturing this multidimensional activity profiles, and we can interpret the results. When we were talking about that latent rank 1 tensors, each rank 1 tensor might be representing an interpretable result, like the weekday activities that we talked about or weekend activities. And we are essentially doing needles in a haystack, few anomalies hidden in a really large data. And we apply it to many different areas. So what are we trying to detect here? Let's look at I have two examples here, the one on the right for a power grid SCADA system, but let's look at the one on the left that I really like. Let's say you have several users, user 1, user 2, and we have Eve here who's going to act like user 2. And each user have a source computer they use to log on to a destination device, like this could be a server, for example. And here, Eve is going to act like user 2, use its own computer and log into Eve's destination computer. So this is an anomaly because usually user 2 does not log into destination device 3 from this source device. It's always normally it coming from source device 2. So this is the type of anomalies we want to detect. And turns out when users in a large network do, for example, authentication events, they create predictable patterns. So in time, there's patterns that we can learn from. For example, here you can see a few users authenticating to a few destination devices and clear work hour and weekday activities, and maybe here's somebody took a vacation, for example. So these are the patterns we want to learn. And we can do that with this CPD decomposition that we just talked about, where you can select an area where you're kind of sure most of the data is expected behavior, and you can factorize this data where your factorization will remove that background noise and keep the important information with these latent factors that we also previously briefly looked at, and it will represent your expected or normal behavior. So at the test time, when you get a new authentication event, you can go into your factors and calculate how likely for this event to happen given what I saw in the past. And we model this under Poisson distribution under the Poisson distribution to get where my p-values will represent the anomaly score, for example. And we apply this to many different areas, from detecting compromised credentials at data collected at Los Alamos National Laboratory, where over 90 days they collected users' authentication events, and there was a red team activity where we want to detect as anomalies. They compromised users' credentials and logged into their computers. And we also looked at botnet traffic and spam email, as well as credit card fraud. But this is a really busy table. There's just a few things we can point out. Our data is massive. We're going all the way up to 6-dimensional tensor. And if you multiply all of these together, it's a lot of entries, right? But recall we're doing Poisson distribution. We only need occurred count of events. So I can just look at the sparse tensor and not look at the entire tensor. So I can just use the occurred entries to model the behavior. So we get extremely sparse tensors that doesn't take a lot of space in the memory, and we can really fast decompose it, although it is a large tensor. The second thing to point out here, we have a lot of entries in this tensor, but only few anomalies that we're trying to detect. So again, needles in a haystack. You can see that as we add more dimensions to the tensor. So here I have a tensor with dimensions user and destination. Here I have user, source, destination. Status is a failed or successful authentication. And I can also add the hour of the day information. But as I add more information, specifically here, the temporal information, tensor decomposition becomes better at differentiating between anomalies and benign activities. So you can see here is the average anomalous score drops to 0.1 from 0.63, while the benign scores are increasing. So you recall, if the low score means anomaly, so it's becoming better at differentiating between anomalies and benign scores. So with this approach, we were able to show that our method, which is unsupervised, does not need labels, does a better job at classifying anomalies than semi-supervised and supervised and unsupervised methods across several tasks, such as botnet detection, spam emails, compromised credentials, as well as, so here I have asterisks here. So fraudulent transactions. Our method, it says we're doing worse than this, a baseline that we compare it to, but the asterisk is they manually balanced their data set, which is not realistic. All of the solutions that we want to work on, especially for cybersecurity, if we're applying machine learning, we need to consider real world scenarios. Therefore, our score is lower, but we need to consider the real world scenarios. And we have also applied this to SCADA systems. And here you can see on the left corner, here's the scores from the SCADA systems, where we compared to two-dimensional non-negative matrix factorization and other dimensionality reduction methods, principal component analysis, and we showed that our method is outperforming it. So tensors are useful for anomaly detection. You can use this software. We have it publicly available with GPU capabilities on this link here. And the data set used in these studies called Unified Host and Network dataset, which is that user authentication activities and host device activities dataset are both available publicly. So it can be utilized as a tool and allow reproducibility of our results. The second application that we're going to talk about today is data privacy. So what is the motivation? So what we looked at here is the recommender systems. So recommender systems are useful because when you go to, for example, Netflix, it gives you a recommendation for a movie, or when you go shopping on Amazon, you get recommendations. There's music recommendations. So it creates this personalized experience for you that is nice. But one issue with traditional recommender systems, and one way to do this is collaborative filtering, is that you send your data to a server that builds the central machine learning model that learns collaboratively from all the clients, all the users, to give recommendations. So you're compromising privacy for this custom user experience that is nice. And there's issues with this. One, if this server is compromised, you lose your private data. Two, there's issues pertaining to, for example, new laws from Europe, GDPR. Sometimes sharing this kind of data is not feasible. So one way to prevent sharing your data is with federated collaborative filtering. That is, you keep your data locally, you train small ML models locally, and you send updates to central ML model that is hosted at this main server. So you're no longer sending your data, but this iterative model updates to train a central machine learning model. So few issues with this. What if somebody leaves in the middle of the training, for example? That is cut off. And many other issues. You keep at each iteration of the model training, you're sending your data. So that takes time. That is slow. And also, there are papers that has shown from this iterative gradient updates that you're sending, you can actually do things like model immersion attacks, reconstruct your original data, learn from the gradients. So you're still, this is not data privacy still, because somebody can still extract your data from the gradients. So one solution to this, which is the solution that we're proposing, is what's called one-shot federated collaborative filtering. So instead of doing this iterative model updates, you send your, you do this training in a single round of communication. And how is that done? So locally, you have some group of users. So this is group-based approach. Think of it as, let's say, collaborating organizations, like two hospitals. They don't want to share their data, but they have this group of employees or patients. They want to use that data to train a local model. So this is for a group scenario. Or you have a household scenario where in the household, there's several people using Netflix, for example. Using this group data, you apply collaborative filtering locally using tensor factorization approaches, and you upload your latent factors. Remember, latent factors were those green and purple and blue vectors that we looked at before. So imagine them like that. You upload these factors to the server. Server collects from each of the client these factors and applies joint factorization to extract joint patterns, which are then shared across all of the clients, which then apply knowledge distillation, which is just a fancy word to say multiply two matrices together to transfer the information. Then you get a local model, which is improved, which is more accurate than the original model that you had with only using the data you had from the current group in the client. And we show that when you, for example, this yellow line here, and we are applying to two movie lens data sets to demonstrate this, is the model that group had before collaboratively learning from everybody. And then the green one here is the model after it learned from the collaborative filtering. And we have the RMSE score. That means we want the score to be lower. Lower is better. And you can see after you apply collaborative filtering, your score improves. So the federated learning is giving you a better local model for recommendations. And compared to our baselines, which may need several rounds of communication, here you can see, let's look at one of them. This FedRec with singular value decomposition plus. They reported their scores at communication round 10 and 100. And it looks like their RMSE score was 0.95 at communication round 10 and 0.92 at communication round 100. Our method only does single round of communication and achieve a lower RMSE score. So it is a useful model where you don't do a lot of rounds of communication and get a recommender system. Okay, so this is the last application area with malware analysis. And here we're going to also talk about that mysterious model that I mentioned in the beginning that can say, I do not know. So why do we want to do this? So malware is a problem. There's a lot of it. In 2020, there was reported 1.3 billion malware specimens, and every month, there's millions of new ones are being reported, and it's an expensive problem as well. When you see large data like this, we think about machine learning, and in fact, it can reduce response time and recovery time, so save time and cost for you. So machine learning can be helpful. But there are certain shortcomings from real-world problems in malware analysis domain that we need to consider. One, these models deployed at security systems, defense systems, need to consider class imbalance. What is that? I don't want my model to just be able to detect prominent malware families that are seen very often. It is as important as for it to detect very rare ones, maybe like really custom-made ones, because those are also expensive, they work. So we want to be able to work under class imbalance. Second, many of the popular models used nowadays are supervised methods that require large quantity of labeled data to train. But in malware domain, labeling data means a security engineer needs to sit down and spend time and look at what this sample is. So it is expensive and time consuming. So our models has to be able to train often with limited data sets. And at the same time, I don't only want to detect malware, but also point out when I see a specimen that I never saw before. So novel type of malware family, for example, because if I can detect, it is one thing to detect a malware, and it's another thing to be able to say, hey, I never saw this type of malware before. You might want to look at it so you can develop mitigation strategies. So the first method that we introduced with this to be able to address this was called random forest of tensors, where you, from your feature set, you randomly sample different features to build n number of, let's say, random tensor configurations. You factorize each of them and use the latent factors. Here we're looking at one of them to kind of cluster specimens. And here, how the clustering happens is the semi-supervised part. The factorization here is unsupervised. But if you look at one of the latent factors, you use your low quantity of labeled data as a reference against unlabeled ones, that's semi-supervised, and perform voting on your sample labels. And at the end, after you do this through each of your random tensor configurations, you do a max vote, let's say, to get to a final decision. This method showed that tensor decomposition can do malware classification, and semi-supervised can help because I don't need a lot of labeled data. So that was a good thing. But it was kind of slow because I have so many tensors to decompose. So we then looked at another approach, which we call HNMFK classifier. This one also worked well under low quantity of labeled data. But in addition to what we did with random forest of tensors, this also turned out to be able to do work under extreme class imbalance. And if you have like thousands of classes, it can still work. So what are we doing here? You have some malware samples and benignware samples, and each one of them has features. Let's say number of strings, file size, byte entropy, raw bytes, whichever feature that you can think of. Here we're looking at static malware analysis-based features, but you can also apply it for dynamic analysis-based features. We factorize this matrix and obtain our patterns from the data. And these patterns are used for clustering, where I don't have labels on some of the samples. Again, using the labeled samples as in a semi-supervised way, as a reference, I will label the unlabeled samples. But I will check the quality of each of the clusters I have. For example, if I have a cluster that is representing only a single malware family, I will say that is a good quality cluster, and I will make a decision. Otherwise, I'm going to say there's two classes of families in this cluster. So there might be mixed patterns. I need to go and try to separate them further. So in a hierarchical manner, I will go and repeat my steps. It was okay in detecting novel families, but it was really good at working on large quantity of large number of malware families, 2,900 malware families that we were able to classify with this. So we needed to also address the other shortcoming. We want to detect novel malware families. So the next method that I will present is called malware DNA. It's a real-time semi-supervised malware characterization method. So we can they simultaneously detect benign-ware, separate them from malware, take the malware and classify it into families, and at the same time identify if there's a novel malware family. So this idea was previously used in the group for detecting cancerous mutations in human genome, and we thought the malware is like also a human genome. It mutates in time. For example, an author might change the code to prevent a security system to be able to detect a malware. So in time it's mutating, right? So we take that idea and apply it to here for malware. We discovered the hierarchical structure of the malware to be able to unmix these mixed patterns across different malware families. And we do this using the methods for Smart Tensors AI. And this method includes what is called reject option. So we'll talk about the reject option in a second, but the summary of the method is very similar to that HNMFK classifier that I mentioned. You have some multidimensional data, you apply factorization, and you get clusters. And if you have a not uniform cluster, a mix of classes, you can go ahead and try to separate the signals again. But if you see a uniform cluster, put your signatures into an archive so that you can use it later for inference tasks. And how is the inference done? When you get a new sample, you project it onto your archive. Let's say we're using non-negative least squares, and it gives you identification or the characterizations of how this sample looks like based on the signatures I have in the archive. But if I see a novel sample, it's going to project it, and it will tell you, I never saw that before. So, and then you can further update your archive for later use. So what is reject option? It is self-awareness for machine learning model to know when it doesn't know. So I really like Einstein's quote here: the more I learn, the more I realize how much I don't know. If knowledge is power, knowing what we don't know is wisdom. So if the model can withdraw from making a decision when it's uncertain, it is useful for places where making a mistake is expensive. It's cheaper to tell the user or security expert, I do not know, you have to look at this more carefully. But more importantly, for this domain, it enabled knowledge discovery. So when your model says, I don't know, that could mean it's a novel malware family. And this method, we can distribute it with HPC systems because when you apply factorization in a hierarchical manner, these are independent components that can be distributed on an HPC system. And we applied to Ember dataset on a small scale experiment. These are preliminary results. We selected some malware families and from this randomly from the dataset, and we selected one of them to represent the novel family. And here you can see with more traditional scores with F1 precision recall, it is performing better than our baselines, which previously used to report state-of-the-art results for the Ember dataset. And in addition to that, rejection novel is essentially how much of the samples do I detect as novel from RAMNet. It is doing a really good job at detecting them as novel. In 2021, there's a paper that argued that that discusses reporting results of a method that can say I do not know with scores like F1 precision and recall may not give you a fair comparison or fair understanding of the method. So they introduced what is called area under the curve of risk coverage to better understand how well your method is performing. So your risk is essentially 1 minus your F1 score, let's say, or accuracy score, and coverage is what is the percent of the samples am I able to make a prediction on? Because there's a trade-off, right? So if I saw a family, let's say Emotet, I should not be detecting as novel, versus I want to detect as much as possible of the samples from RAMNet as novel. So there's a trade-off, and that's what it's demonstrating. And the area under the curve for this should be a low, so having a lower number is better here, and we get 0.02, which demonstrates that we can have low risk with a high coverage, which shows that the method is performing well on this specific experiment. But we also showcased if you increase in this x-axis here, I have the fraction of unknown malware families in my analysis, and my x-axis is my average F1 score, and I have the confidence, 95% confidence interval there. And what we're showing here is, as you reduce the amount of labeled data you have all the way down to only having 5% of the data for training, it is continuing to maintain its performance. And that is thanks to the reject option. We recall we mentioned is one of the shortcomings that we have to address. So these codes are also available publicly, so you can replicate our results and utilize it as a tool. Here I have the link. With that, thank you so much for your time and attention. Please let me know if you have any questions.
All right, thank you so much for the great talk. Audience, if you have questions, please put them in Q&A. We have one question. Can you explain how the model handles the introduction of new families of malware? Will this degrade the results over time?
Thank you so much for the question, Nicholas. So how is the, let me try to see if I can answer. So you have this signature archive, which is built from this latent patterns that we talked about from your multidimensional data set. And when you get a new sample, and I know I'm abstracting a lot of math here, but I'll be happy to share my paper as well. But when you get a new sample, your features are being projected onto your archive using, let's say, non-negative least squares. And once you have this projection, you can use similarity metrics to compare each of the other signatures you have on the archive and see if any of the signature similarity score is above a threshold that you defined. And if it is, you make a prediction. But if it's not, you can say, I am rejecting to classify. So the reject option has been studied under uncertainty quantification, anomaly detection, and adversarial ML. But the reject option combines all of these fields and introduces things like discriminative ability of your model. You want to have the model to be able to say if it's as much of the samples in your novel family detected as much as of it novel, but also how much are you making a mistake of the things that you knew that are now being classified as a novel, and how accurate are you in classifying things into known classes. So you optimize your model for that. So that's why it's called the reject option. And does the results degrade over time? That's a really good question, and I think that might be open research question. Can you take the samples based on your timestamps and look at the model as you go in time and see how the results change? We have not done that experiment, but that's a really good experiment idea, I think. What I can say is a hypothesis based on the results we have for the quantity of labeled data. The reason why the model maintains its performance relatively as you reduce the amount of labeled samples you have is because it increases the amount of rejections it does. So if in time you're not adding this new information in your model, perhaps it's going to behave like this, where the performance does not degrade, but you are worst at covering more samples. And recall coverage score was how much of the samples am I predicting instead of saying I don't know. So that would be my hypothesis for the second part of the question. But I will say I do not know because we have not done that test and I am rejecting to answer essentially.
Thank you. Do you have a wild guess? All right. I think that was the only question.
Okay. Thank you so much for your time. Here's my references. I'll slide through them. Yeah, thank you so much for the time and
Thank
the
you so
opportunity.
much.
Okay, have a good day.
Thank you.
Thanks, Maxim. Take care.
Take care.